these webinars. It's really a fantastic initiative and allows us to talk a bit while being confined all in our homes. So that's fantastic. So the way I want to do the presentation, I have a presentation I will give, but at any point, as Tommy said, if you have some comments or questions or suggestions, feel free to interrupt, like raising your hand or typing something in the chat. And yeah, we can. It's not a fixed schedule or lecture in that sense. I just want to share some ideas with you as to how I usually communicate climate change adaptation. And I do that in different settings. Very often it's in university courses, which can be at undergraduate or graduate level for people who are natural scientists or medicine students sometimes, or people in environmental sciences, undergraduate, graduates. And very often we also give presentations during research projects, which then are either for colleagues or administrators or for the general public. And yeah, I mean, sometimes people are already quite aware of climate change, especially in coastal communities. So they actually know most of the things that we're talking about, but I try always to give a little bit broader perspective as well, geographically as time-wise, to go back a bit in time and see how sea level rise has evolved in the past, and to see how we're not going to talk much about adaptation today because the focus is really on the science of sea level rise, but adaptation is the same. We can look at what people do locally, but it's also interesting to see in other countries how people adapt. So I hope everybody believes in global warming and we don't have to wait for our homes to be flooded. That used to be like 10 or 15 years ago when people started doing projects in Quebec or New Brunswick. That could always be a concern at public hearings, that some people would contest the whole basis of climate change, and then that makes it really hard to talk about sea level rise, since it basically derives from that and all the other phenomena. I think by now, in Canada, I really rarely, or at least in maritime Canada or in Quebec, I really rarely had anyone who contested the science of climate change as a whole. Of course, if you're in the US, we have someone from the US, right? I'm not too sure what city you're in or what coastline, but in the US, of course, it's a different issue, and even in exposed communities, sometimes people don't believe in climate change. So that makes it really hard to do any action on adaptation if you don't accept the principle. So of course, one good way always to start talking about coastal risks and sea level rise and climate change is to show some of the events that have happened in recent years, such as here that's a picture from New Orleans, 2005, the Katrina hurricane, or a couple of years later, there was the Sandy hurricane on the eastern seaboards, that's in New York, I believe. More recently, were the big floods in Houston due to a stationary hurricane there for a while. And of course, in New Brunswick, we had the storm of 2010 that especially, who was it again? Jolene, no? Who's from the Shediac region. So that's a picture somewhere very close to Shediac that was taken by the people from the Commission d'Aménagement. So that was a storm that really showed people the vulnerability of our coastline to changes in sea level. And it was a big storm. So one question that always comes up is, and if you've seen Al Gore's documentary, what's the name again? An Inconvenient Truth. That's one of the images that we can see in the documentary, and there's a picture of an American city. I'm not sure if it's New York, doesn't look like it, but with a 6 or 7 meter sea level rise. And then the question is, well, will the sea level actually rise 6 or 7 meters, or how far will it go? So that's a good question, to which actually there isn't a simple answer. It really depends on how far you look ahead. So we'll examine some of that. And other questions that are commonly occur is, why does the sea level rise? And I see there's a T missing there. And has the sea level changed in the past? And what did that mean for human communities that lived at that time? And how far will sea levels rise in the future? So I'll try to give some elements of response to all those questions. And if you have other burning questions, we can surely talk about them too at some point. So if we look at the more recent past, and when we talk about recent, that's of course in geological terms, not necessarily in human terms, but if we look back at the last 3,000 years, we know that the sea level has increased very, very slightly, which is still a long-term consequence of the deglaciation, has increased by about 0.1 to 0.3 millimeters a year. So very, very slightly. And suddenly, so that's the blue line very at the bottom there. And if we look at the upward going arrow, we can see during the last 100 years, suddenly that rate has increased to 1 to 3 millimeters per year, which is a tenfold increase. So there's been a dramatic increase in sea level rise over the last century. And with the newest available data from 1992 until now, which is based on very precise satellite measurements that didn't exist before, we see that we're exceeding that rate. It's about 3.3 millimeters a year. And actually most of recent research shows that this sea level rise is increasing. The rate is increasing. So maybe we're even higher than 3.3 millimeters a year now, and it keeps increasing. So of course, that's something that definitely worries scientists and coastal planners everywhere in the world, because we have an increasing level of sea level rise. And we don't really know how far it's going to go and how long it will keep increasing like that. Of course, if we look back in the past, so before 3,000 years, the sea level has increased and decreased multiple times during the Earth's history. And during the more recent history, let's say the history of human civilizations, since the last ice age, there's been considerable differences in sea level rise due to the fact that at the heights of the last ice age, there were 3 to 5 kilometers of glaciers on many of the land masses in the Northern Hemisphere. And that, of course, took the equivalent of something like 120 or 130 meters of water out of the ocean. So the sea level was much lower in those days. And if we look at a map of, let's say, like 10 or 20,000 years ago, we can see that there's almost those orange areas in the map, which are areas that were dry lands at that time and which now are submerged. And this had considerable consequences for humans who lived at that time. If you look at the very, very bottom of the map in Tasmania, which used to be connected to Australia, but during the deglaciation, around maybe 6,000 BC, Tasmania got cut off from the Australian continent, and then there was an isolated population of Tasmanian Aborigines that persisted there for about 6,000 years until Europeans came and tragically wiped the whole population out by either killing them or deporting them. And the same goes with New Guinea, that got disconnected from Australia 7,000 years before now, or before our time. So that would be about 9,000 years in the past. So those populations all after that evolved independently of each other. And one thing that's really amazing is that in old Australian Aboriginal oral transmissions, there are actually some oral transmissions that scientists were able to connect to events that happened during the deglaciation, and found actually geographical evidence that those were real tales that have survived all this time until nowadays. They talk about the inundation by the sea, and that probably are about 7,000, 8,000 or 9,000 years old. So that's really mind-boggling that the memory of these events has persisted so long in those populations. And if you look at the very top of the map, we see a landmass between Alaska and Kamchatka that's called Beringia, which was basically almost a continent the size of Alaska that existed for many thousand years and was inhabited by populations at that time. And these populations can be directly related to First Nations populations that live nowadays in North America. So many scientists believe that this is the way that initially North America was inhabited by humans, and there was really a direct link between those populations. So I don't know, Tommy, you wanted to add some comments on that? theory about the population of North America?
Oh, we just had so yesterday was the French presentation, and we had a really interesting conversation about how there are likely multiple ways that people would have arrived, and just also thinking about the importance of creation stories and how identity plays so strongly in that, and the ideas of peoples that have didn't exist as the people that they are until they became connected to the land that they are currently stewards of. It was a really interesting conversation.
Okay, yeah, thank you for that input. So definitely sea level rise in the past has affected human populations, and the same is true for Europe. If you look at, that's a little animation that was done by the University of Moncton, the evolution of sea levels from 20,000 years ago to basically present sea levels. You can see that 20,000 years ago, England, or the UK, well, that didn't exist at that time, and Europe, the mainland, were connected. It was just like one landmass. And about 7,000 or 8,000 years ago, they became disconnected. And from then on, the populations in the British Isles have always been somewhat different from the ones in Europe, and back and forth travel has not been very easy until they constructed the tunnel a few years ago. And there was also one very interesting area that's called a Doggerland, and I'm not sure if you've heard about this before, but that was a whole big geographical area that was inhabited in the Mesolithic era, and that existed in the north, in what is nowadays the middle of the North Sea, like somewhere between Denmark, England, and the Netherlands. And that was actually, that disappeared in the ocean around 6,500 to 6,200 BC, and was then completely forgotten about, and people didn't even think it existed until it was rediscovered in 1931, and they found lots of human remains and jewelry and weapons and mammoth tooth. So there was big fauna that was walking around there. So that's a whole area of Europe that was extremely prosperous in the Middle Stone Age, and that's then completely disappeared under the ocean. And of course, sunken cities and all those kind of events exist everywhere in the world. That's one example that's very interesting from the north coast of Germany. There was a legendary city, or it turned out not to be legendary, but the city of Rungholt in northern Germany that was supposed in the early Middle Ages to be an extremely rich city, and was then completely devastated by a storm in 1362, the Marcellus storm. And afterwards, it like became a legend. People didn't, after a few centuries, people didn't think it had actually really existed. So it was just like a fairy tale. And suddenly in the early 20th century, some fishermen started finding interesting archaeological remnants, and eventually archaeologists could reconstruct that there was really a whole city that had existed in that area. And if you compare the two maps, you can see that there's a whole part of all these islands that had completely disappeared in the ocean. Sometimes related to sea level rise, but sometimes they're just related to coastal erosion and catastrophic events that happen. So not everything we see in terms of erosion and flooding risks is necessarily related or caused by sea level rise. That's also something we have to consider.
Sebastian, if I could just ask everybody, how is the sound doing? I see somebody's typed in the chat that it's low. I'm wondering if that is something that other people are experiencing. Can everybody hear okay for the most part? Okay. Oh, sorry, Kirsty, that was me. I will make sure that I'm better in the future. Sorry about that. Thanks, everybody. Are there any questions or comments so far? Is there any, has anybody had any strategies that they'd like to share about how to communicate this to potential students or the public? Okay, bravely onward. Thank you so much.
Okay, thanks everybody. Yeah, so what happened since the last glaciation that in the last 10,000 years or 20,000 years, if we think about it, it's really the the time of most of human, or at least the history of civilization as we know it. So as you can see from those coral records here, which are a good indicator of sea level rise, because corals always have to be at a very fixed depth just below the water surface. So we can see that the sea level rise has risen about 120 meters over like a period of a couple thousand years. But you can also see at the very top of the picture there, once you reach the 6,000 years limit, maybe, if I could say, it's been fairly flat since then. So in the like recent history, sea levels have not changed very much. So the fact that they start change again, of course, changes a lot for human habitations. So we're going to talk now about today's sea level rise, what's happening now and why it is happening. So there are two reasons for which, related to climate change, for which sea levels are rising. One is the thermal expansion of the ocean, and the other one is glacier and ice sheet melt. I'm not sure if you were familiar with both these terms. Probably most people will understand easily the glacier and ice sheet melt, that would just pour water in the ocean and it will make it rise. The thermal expansion is a bit more tricky to understand, but thermal expansion is actually a phenomenon that we're rather familiar with, even if we don't think about it. One example, it's any structure that's made out of metal. Well, metal changes its size quite a bit with temperature. So one very big structure that's made out of metal is the Eiffel Tower in Paris. And that actually changes its height quite a bit from warm weather to cold weather. So during hot summers, it can like grow by about 20 centimeters. And during cold winters, it can shrink by 10 centimeters. And that is a direct consequence of thermal expansion. And the same is true for concrete and roads and bridges. You will often see that there are some gaps that are left before and after bridges. That is to like provide a safety margin for the fact that during very cold or very hot weather, the concrete or the metal of the bridges will shrink or expand a little bit, and some space is provided for that. And that's the same phenomenon really for most liquids. Some liquids have a very strong thermal expansion, like oil, for example. If you make an oil bath and you fill it to the very top with cold oil and then you start heating it, there's a good chance that the oil will just overflow your bath. Mr. Cat, you're not welcome. Okay, and another liquid that does that is mercury, and that's how thermometers used to work. That when it was very cold, the mercury in the thermometer contracts, and so it indicates a low temperature, and at higher temperature, the mercury expands, and then you can read the higher temperature. And water does the same, but it actually contracts and dilates very little with temperature. The thermal expansion coefficient, that's the scientific measure of how much it expands with a temperature increase, is 69 times 10 to the minus 6 per Kelvin. And Kelvin is the same as a degree, really. It's the same unit as degrees. So it basically expands by 69 millionth of its length per degree that you heat water. So obviously, if you just place a cup of water in a microwave and heat it, it's very unlikely to overflow, and you wouldn't see the difference really. But of course, the ocean being really, really large, the average depth of the ocean is about 4,000 meters. 69 millionths of 4,000 meters makes quite a bit. So the calculations on the left here, you can calculate with that it would be something like 27.6 centimeters per degree increase in ocean temperature. The ocean would rise by 27.6 centimeters, which obviously is not a lot compared to the 4,000 meters that it has, but compared to the position of the coastline, something like 28 centimeters can make quite a difference. So that's how thermal expansion works. It's actually a very simple principle. Is that clear for everybody, or maybe you all knew it before? Okay, and I don't know if I can Yesterday I found a way to have the chat open at the same time. Now I don't see it.
Oh, if you take it out of full screen.
That's how it worked, huh?
Yeah. Or you can still be in presentation mode, just your screen out of full screen. Thank you for bearing with the tech difficulties, everybody.
Yeah, no problem. I still can't find the chat now.
The chat will be a button at the bottom.
Yeah.
Yeah,
Well,
the Eiffel Tower is very descriptive, isn't it?
Yeah, and well, it doesn't work that well on my screen. But maybe if there's a comment, then you can just like read it and interrupt me.
Well, I don't want to be too rude.
No, it's not rude. I'd be glad to answer questions or take in comments.
Okay, for sure.
The second aspect, which is the melting of continental glaciers. And here you see a graph that shows the cumulative mass of ice sheets and glaciers. And you can see that since like the 1950s, there has been a pretty much continuous decrease in glacier mass. And as you see towards the end of the curve, that's even accelerating. So glaciers are melting more and more quickly. And people everywhere in the world that live in mountainous areas can see that. For example, so that's always a good tool to illustrate the melting of glaciers and the impacts of climate change, is to compare historical photos of glaciers with more recent photos. And there's a lot of collections of those kind of presentations you can find on the web everywhere. I'm just going to show you a few of them. Like this is a site in Austria, somewhere. Ötztal, where the famous Ötztal person was found. Ferner Gletscher. So you can see the upper pictures are like a few decades ago, 1926 or 1935. And if you compare how these houses in the background look nowadays, you can see that the houses may have gotten a little bigger, but the glaciers definitely have retreated in a quite spectacular fashion. And that you can see in other places in Europe too. If you compare the upper picture in 2003 with the lower picture in 1890, that's somewhere in Germany. The Zugspitze might be the highest mountain in Germany. But it also happens on other continents, like in Patagonia, so in the southern tip of South America. You can see very spectacular differences in glaciers that have completely disappeared, or in the Andes, that's the lower two pictures, where there's also a retreat of mountain glaciers. In Africa too, there are a few glaciers in Africa, a few high enough mountains to have glaciers, like the Kilimanjaro, which is extremely famous, but has in just a couple of decades retreated significantly, and the glacier there might completely disappear within a few decades. And one of the regions that has warmed the most in the whole world is Alaska. And there's a lot of historical photos that have been made in Alaska about glaciers. Here you can see 100 years difference exactly on the Carroll Glacier in Alaska, 1904. And if you compare with nowadays, you can see that that glacier has completely disappeared out of sight. Or another image from 1899 of Muir Inlet in Alaska, compared with nowadays, that too has completely disappeared. And even less recent photos, that's a USGS photo from 1941 of Riggs Glacier. And you can see that all that glacier has completely melted and now forms a glacial lake. So that's very spectacular images and shows a bit how climate change is already changing our landscapes. And of course, all that water that used to be in the glaciers, so the ice has melted and then makes glacial lakes, and those glacial lakes will eventually reach the ocean. So all that water will reach the ocean and contribute to a sea level rise. And now a special case are the big ice sheets, which exist in Greenland and the Antarctic, which are basically just a big collection of glaciers, but since they're so huge, scientists tend to treat them in a separate way. So obviously on the map, you can see them very well as the white spots at the very top of the world and at the very bottom of the world. So at the top, that's the Greenland ice sheet. Very bottom, it's Antarctic. I'm not sure any of you has seen any of those before. I know some people that have been on Antarctic cruises, but I certainly haven't myself. I've flown over Greenland once on the way from Europe to Canada, and it's very spectacular. But those some parts of those ice sheets are actually becoming unstable and starting to melt. So the dynamics of an ice sheet is, in its detail, very complicated, but in its basic principle, it's actually quite simple. That at the top of the ice sheet, there is precipitation that happens usually in the form of snow or just condensation. There isn't any rain because those areas are way too cold to have rain. And that humidity that precipitates on the glacier will get frozen and contribute to the growth of the glacier. So if there wasn't anything else, glaciers would just like grow and grow and grow. But what happens is that those glaciers usually flow into the sea, and at the so at the interface of ocean water and glacier, there's a transfer of heat, and the ocean water usually being around freezing point, sometimes a bit over, sometimes a bit lower, will warm the glacier and will make the glacier melt. And then icebergs fall into the sea and get transported, and so the whole calving phenomenon. So that's how glaciers how glaciers live, as a very simplistic view. There's a lot more complicated phenomena, but I think for most people that's really not important to know about glacier lubrification and those kind of phenomena. But just it's important to understand the basic principle that glaciers can grow by an increase in humidity and accumulation, and can decrease their size by melting at the edges. And with climate change, both actually happen. So there are some parts in the Antarctic ice sheet that are increasing their ice mass just because there is more humidity in the atmosphere, and it makes more precipitation, condensation on those glaciers. So some parts of ice sheets actually are gaining in mass, but other parts of the ice sheet, especially in the western Antarctic parts, are losing a lot through glacier melting and calving at the edges, much more than they accumulate. So they're actually decreasing in size. And in the case of Greenland, that's a photo of Greenland, so it's really huge. And Greenland has experienced really record melting over the last years and maybe even decades. So Greenland is losing a lot of ice, and all that ice goes straight into the ocean and contributes to a sea level rise. If the whole of Greenland was to melt, as you can see in that computer animation here, well, it's not an animation, it's just pictures, that would be equivalent to something like 7 meters of sea level rise, which is a huge number. However, that is not something that happens overnight, like in some catastrophe films, you might see that. But that would take a few thousand years to entirely melt. But the problem is that once the main glaciers have become unstable in Greenland and in other parts too, it's very hard to stop the melting. So even once the process has started, and even if temperatures were to go back to what they are nowadays or were like 100 years ago, it would not necessarily stop the disappearance of the ice sheet. So there is what scientists call tipping points that exist somewhere in the system, that beyond a certain temperature, the ice sheet just becomes unstable, will start melting, and then the glaciers start flowing, and that's pretty much an irreversible process. And that's one of the reasons why scientists always insist on the importance of limiting climate change to like maybe 2 degrees at most, or 1.5 for some, because once you go over those tipping points, we really commit to certain phenomena that we can't control after that anymore. And ice sheet melt is one of them. And in the Antarctic, it's not the whole of the Antarctic that is at risk of melting, because the whole of the Antarctic continent has the equivalent of about 20 meters of sea level rise in it. So that would be huge, but that's been stable for like many tens of millions of years. But there is one part that's to the left in the picture that's called the West Antarctic ice sheet, so beyond the Transantarctic mountains, where in the little inlet you can see the Ross ice shelf and the Ron ice shelf and the Filcher ice shelf. Those are all glaciers that flow into these big bays. And those are unstable, and we know in the past that in previous interglacial periods, that was slightly warmer than ours has been up to date. That has actually melted to a large extent, and the sea level was higher than today, and that could happen in the future. And that's an estimate of about 6 meters of sea level rise that is contained in those parts which are unstable. And that too, like in the case of Greenland, it's not something that will happen next year or next decade or even in the next century. That takes several millennia to melt, but of course, it still contributes quite considerably to what we see nowadays in terms of sea level rise. Okay, I hope that was all clear, or maybe you'd heard all of this before. Now, one thing that we often tend to confuse, it's the alarming news about the disappearing of the Arctic sea ice. And if you see pictures, a comparison of September 1984, so the end of summer, and September 2016, so that's kind of the minimum extent of it. You can see that it has indeed decreased very dramatically in just a few decades. And that has a lot of consequences for Arctic life. And so, for example, species like polar bears or seals that need ice shelves to hunt or give birth on, well, they don't have that much of it anymore, and that really affects them. It has an influence on ocean currents, on the thermohaline circulations through the formation of deep waters. It also affects the Earth's albedo quite a lot, since the sea ice reflects a lot of sunlight, and when the sea ice disappears, it's replaced by ocean water that's very dark and absorbs a lot of the sun's radiation, and that heats up the Arctic a lot. So that's one of the main, if not the main reason why the Arctic warms so quickly compared to other places on Earth. It also has effects on the navigation. So if you think of the northeast or northwest passages that might be passable within a few years or decades. However, it does not have any influence on sea level rise because that is ice that is already floating on water. And there is the famous principle of Archimedes that you might remember from school. And I found it always very difficult to explain, but basically it says that a floating body displaces a volume equivalent to its mass density. So ice being somewhat lighter than water, the density is about 0.9 grams per cubic centimeter compared to 1 for water. Most of the ice is under the water, and just about like 1/8 of it is immersed. But what happens is when the ice melts, it gains a density that is exactly that of water, since it becomes water, and it displaces exactly the same volume of water than it did as an iceberg or as an ice sheet. So and the same is true for ships, for example. Ships only float because their density is lower than that of water due to the fact that they're filled with air. So if you fill the ship with water, it will no longer float, as the Titanic tragically experienced. So one experiment that you can do if you're not convinced by this is if you like to have a whiskey in the evening, you can pour yourself a glass of whiskey, put some ice cubes in it, and put a mark at the whiskey level. And if you're patient enough to wait for all the ice cubes to melt without drinking any of the whiskey, you will see that in theory, the water level should not change once the ice has melted. And if you do that in a class, you can just do that with a glass of water, put some ice cubes in it, and if the class is long enough and the classroom is warm enough, it will have time to melt entirely by the end of the class, and there should be the same amount of water in the class than before. So that's really a simple experiment that can demonstrate the Archimedes law. And that's the same law that explains why changes in sea ice have no effect on sea levels, which we sometimes think, but it's a wrong misconception we have.
So I'd just like to break in and just check that everybody's all doing well on the same page here. We can spend more time on the presentation. We have about 5 or 10 minutes left to keep presenting, if that's useful to you. We can also focus less on the presentation and go for more discussion if that's helpful. If you could just let us know in the chat as we keep going, that would be great.
Yeah, I have a few things I can add. So the different causes which contribute to sea level rise, you can see that the current contribution that's in red here, most of what we see nowadays in sea level rise, it comes from small glaciers and ice caps, and Greenland contributes quite a bit, and the Antarctic, so far not so much. But if you see the white squares, you can see that the potential contribution, the white rectangles, I should say, the potential contributions of the Antarctic and Greenland is much, much bigger than that of smaller glaciers. So in the future, they will probably play a much bigger role. And talking that we can just skip over. So one question that's always, of course, a major question, and also for planners, is like how far will sea level rise actually? And then we usually go looking into the IPCC report and see that each IPCC report updates its predictions on sea level rise. In the latest one, you have 4 different scenarios. So the 4 colors there represent different greenhouse gas emission scenarios. And of course, the more greenhouse gases we emit, the stronger and faster sea levels will rise. And but one thing that is important to understand about those predictions is that they do not include, I think I've written that, they do not consider the acceleration of ice sheet melts. And you can see that the contribution of ice sheets has a huge potential, and we see that sea level rise is accelerating nowadays. So those are rather optimistic estimates. And if you read the whole of the IPCC report, which of course is it's super long and very technical, and then not many people will read it or understand what's written in it. We included for lots of it. They warn that this is indeed just a projection that does not include certain feedbacks, which could dramatically increase the estimates. So here I've made a little compilation of different estimates that exists from the top 3 are different IPCC models. And then there's a range of different models that are not based on like mechanistic models, but they're called semi-empirical models. And they basically compare in recorded history, geological history, the relation that existed between sea level and either temperature or either radiative forcing, so the amount of greenhouse gases in the atmosphere. And we can see that some of these publications come up with much higher numbers by the year 2100. Some go even up to 2 meters. And those are all very famous and respected scientists. So it's definitely a very serious literature and something to really take into account. And this is an interesting little graphic I found in a book by David Archer, who's a, what is he? Oceanographer, chemical oceanographer from Chicago. That's called The Thaw, How Humans Are Changing the Next 100,000 Years of Earth Climate Change. So they're a very interesting book to read, and actually very understandable for non-scientists or scientists in a different field. So I had no trouble following the book, even though I'm sure his scientific work is very hard to understand. But you can see today where we are. And so to the right, it's the different, horizontally, it's the difference in temperatures, and vertically is the differences in sea levels. And if you look at the last interglacial period, so that was about 120,000 years ago, before the last glaciation, there was a period just like ours, where for maybe 10, 20,000 years, there were no big glaciers. And that last interglacial was a little bit warmer than ours, but not much, like 1 or 2 degrees. But sea levels were quite a bit higher, 6 or 7 meters higher than nowadays. And that's kind of 1 or 2 degrees warming. That's pretty much exactly where we're going. And some remnants, if you've ever been to the Caribbean islands, you can see formations that are called iron shores, which are basically fossilized corals, but which are emerged from the ocean. And the reason for that is that they actually come from this last interglacial age where sea level rise were higher, and they're a few meters higher than nowadays corals. So that's actually 120,000 years old coral fossils that existed at that time, and you can still see very sharp rocks, impossible to walk on. And if you go a bit further in the past, we come to a time that's called the Pliocene, which is somewhere around 3 million years ago, like 2 to 5 million years ago. And that period is interesting for one reason. It's because the concentration of CO2 was around 400 parts per million, CO2 being the main greenhouse gas in the atmosphere. And that's about the concentration we have nowadays. We actually exceeded 400 ppm, so parts per million, a few years ago. And at that time, sea levels were much higher than today. They were 22 meters higher than today. And the continents were pretty much in the same place than they are nowadays, with a few differences, like South and North America were not connected at that time. So that's a bit worrying when you see that with the amount of CO2 we have in the atmosphere nowadays. In the past, there's been 22 meters of more of water in the ocean. That gives us an indication. And just to give a perspective of human history, our ancestors that lived at that time, if you remember the friendly looking lady on the picture, that's Lucy, the Australopithecus. That's sometimes called one of our earliest precursors. So that was the closest to humans that existed at that time. So that's the last time in like Earth history we know that there has been that much CO2 in the ocean, in the atmosphere, pardon. So one graph that I find very important to understand the importance of time scale and how things evolve through time. The yellow graph here, or orange if you want, the CO2 emissions, you can see that at the very beginning to the left of the graphic, there is a peak of CO2 emissions. So at any time in the next 100 years, hopefully very soon, we reach a peak of CO2 emissions and then decrease our CO2 emissions. It will take, and that's the sort of purple graph you have there, the stabilization of CO2 in the atmosphere takes about 100 to 300 years after that. And the pink graphic over that shows you the stabilization of temperatures. That also takes a few centuries after we stop emitting CO2 in the atmosphere. And then you have the sort of strong blue curve that goes upwards and decreases slowly. That's the part of sea level rise that's due to thermal expansion. And that keeps going for several centuries to about a millennia, which is due to the thermohaline circulation. That's basically the mixing of the ocean through ocean currents and deep water formations. And it takes about 1,000 years for the ocean to be completely mixed. So that part of sea level will still keep going for 1,000 years. And then you have the pale blue curve that goes upwards and upwards and upwards. That's the sea level rise due to ice melting. And that, as I said before, that's a phenomenon that, especially when you consider the large ice sheets, once it has started, there's really nothing that will make it go back anytime soon. So that will continue for thousands of years. So the question we asked in the beginning, that we also want to know, well, what will be the sea level rise by 2100? Will it be 1 meter? Will it be 50 centimeters? Will it be 1.5 meters? We're not really sure. And of course, it's an important question for planners, but it's also a very narrow view of sea level rise, because even after 2100, that's a few generations from now, but even then it will continue for hundreds and thousands of years. So that's something to consider. And of course, when we look at those really, really long timelines, it doesn't really mean much in terms of our planning of where we want to build a house or where we build a dike. But on the other hand, I mean, many European or Asian cities are several hundred or thousand years old and are still there, and we still inhabit them. So I think it does have a relevance to look that far in the future. So that's the most important things which I had to say. I don't know how we're in time, or if it's better to go.
Yeah, I think it's a great time to start discussion. Yeah.
There's a few other things. I can leave it on the PowerPoint, like about how sea level rise don't change uniformly over the Earth's surface, but
well, while we're, why don't you just do a quick run through the last of the examples?
Maybe this one, the isostatic rebound, because that's something that's important in Canada and North America.
Sure, and while you're doing that, we can get the tech support, yeah, Jessica, to unmute everybody so that everybody can have that power.
Fantastic. So that comes from the fact that there used to be very large ice sheets on the North American continent, and actually Europe the same. And once those ice sheets disappear, the whole weight of them disappears. And then the Earth that had been depressed quite a lot, as you can see in the upper picture, there's moves back upwards. And that's what you call the isostatic rebound. It's a bit like if you had a sheet that some people were holding, and you put a bowling ball in the middle, it's going to go down quite a bit. And if you take the bowling ball out, or a trampoline, for example, it will rebound. And just to get an idea of how big those ice sheets were, if you're from Seattle, it would be the equivalent of 1, 2, 3, 4, 5 of the, I don't remember what it's called, this Tower of Seattle. I was there 2 years ago on it. Or the equivalent of 3 Eiffel Towers, or if you're from Montreal, it's the equivalent of 1, 2, 3, 4, 5, 6 Olympic stadiums on top of each other. And that's all solid ice. So they were incredibly heavy and have depleted the continents by tens of meters. And now there is, so in all areas where there were those ice sheets, especially around Hudson Bay and the whole of the northern part of the continent, there was a rebound and the land rises. And on the edges where the ice sheet stopped, that actually got lifted up a bit, and that's now sinking back into the sea. And if you look at the red arrows is what goes up, the blue arrows is what goes down. And if you look at the little inlay there, where you have a bit more detailed picture of Atlantic Canada, you can see that we're really very much on the edge of the old ice sheet. In some parts, like the northern Quebec, it's like rising still from the ocean, but other parts such as the Côte Nord or some parts of Prince Edward Islands, for example, it tends actually to sink a little bit in the ocean. It's not huge numbers, but all of this contributes to relative sea level rise. So if the continent sinks, of course, it appears to us as if the ocean was rising, and those two go together. So, and if you want to know more about this phenomenon, you can read the publications by Réal Daigle, who's a famous consultant in New Brunswick, has done a lot of really great work on the relative sea level rise. So that's pretty much it. I'll leave it.
We have a few people ready to talk. Let's go alphabetical here. First Adam, then Brandon, then Kate, and then Leanne.
Awesome. Yeah, thanks. No, thanks for the talk. That was a great summary. And I'm just wondering, for communication purposes, like I really like the Eiffel Tower example. And one of the things, I know you mentioned the bowling ball and the paper example, but one of the things that I've always struggled to give kind of like a practical example of to describe that the kind of land subsiding piece, especially in Atlantic Canada, and how the land's sinking. I guess I've just struggled coming with an example for that. So I was wondering if you've used other ones in addition to your kind of bowling ball on paper example to describe that.
Yeah, I mean, I think one thing I find that I try while communicating climate change is always using a lot of pictures and graphics and stuff, because that's something we understand a lot better than abstract talks, and to relate to, of course, things that's, especially when we work in communities, there's lots of stuff that people have observed by themselves, so that to relate to that. And yeah, I don't have necessarily great examples or experiments or mind experiments for every aspect of what I was talking about, and maybe some of you have some ideas about that.
So I'm realizing there's more than one person named Brandon Love here, or maybe it was just a link that was shared. So one of you has your hand up, and I'm not sure if your name is actually Brandon, but go ahead.
Oh, hi, that must be me. It's Rob Capozzi. Do you hear me?
Yeah, Rob. Hi, nice to hear from you.
Oh, thank you very much, and great session. I think because Brandon linked me in. Sebastian, thank you very much. I wanted to ask you: is there any scientifically agreed upon cause for the 400 plus parts per million carbon in the atmosphere during the prehistoric age that you mentioned?
Yeah, I mean that's a very good and very long question, because of course you know that for the recent past, and by recent geologies mean something like a bit less than 1 million years, we have the Arctic Antarctic ice drillings that give us those bubbles where we can very precisely in the ice cores measure the amount of carbon dioxide. So that's extremely precise numbers up to roughly a million years nowadays. If you go further than that in the future, it's always indirect evidence. So it can be from isotopic ratios in, I don't know, foraminifera or in rocks or different rock formations that existed with different amounts of carbon in the atmosphere. So of course there's a lot more error margin. And when I say or someone says it's about 3 million years ago, it could be 2 or it could be 5 million years ago. So it's much less precise than modern measurements. But there's still some geological evidence that that's roughly about what the CO2 was at that time. And it has even been higher in the past before due to different geological and biological phenomena. Mm. But I could probably find you some more detailed literature on that if you're interested. I don't have
no, just wondering if there was some high volcanic activity, or if Lucy had discovered matches or something like that.
Yeah, I wouldn't blame Lucy for it, but definitely there has been some episodes of really high volcanic activity during the Siberian traps or the Indian traps, which did first for some million years emit huge amounts of CO2 in the atmosphere. But then also cause huge weathering, which tends to decrease that CO2. And what has changed the concentrations a lot is also, but that's longer ago in the past. It's of course the emergence of vegetation on the continents, which didn't exist at some point. So there were tons in Earth's history, which was much warmer than today, like 300 million years ago, maybe.
Okay, thank you very much.
Awesome. Next we have Kate and then Leanne.
Hi, can you hear me?
Yes.
Okay, great. My name is Kate Watrous, and I'm the National Volunteer Program Coordinator for Parks Canada. And we've been adapting some of our, it's less of a question and more of just a comment. We've been adapting some of our selfie stands so that people can take iconic photos of themselves in front of beautiful places, but we've been adapting them to some citizen science applications where we're using them to monitor things like forest fire regeneration, as well as, I'd never thought of glacier monitoring, but obviously that's something that we should look at. But it's a really important way to connect volunteers with these larger climate change issues. And then, so the impact that it has on them is not just giving us data that we can use and that we can share with researchers, but it also has an impact when they go home, when they're thinking about the choices that they make and how that's contributing to climate change. So I've just been really interested by this discussion, and I'm really inspired to try some new things. So thank you very much, Sébastian.
That's a really fantastic idea. I love it. And for example, a few years ago, I was in, what was it, glacier? I don't remember, in Alberta, the one big glacier that people always visit.
Columbia?
Yeah, exactly. Thank you, Columbia Icefield. And it's just amazing when they show you the pictures of when they had tours in the 1920s or 30s and how much less ice there is. And that, I think, really like sensibilizes a lot of tourists to the fact that our ice sheets are disappearing really rapidly, and that's something we can see in like one human lifetime very easily, especially in Alberta, where people are sometimes more doubtful about the existence of climate change. But when you can see, of course, it's always shortcuts, right? Because the glaciers have been melting before climate change, and there's been periods in the 1930s and 40s when there was glacier melt, and we're not sure it's because of climate change necessarily, but still to think about all those, the link that there is between our environment and climate change, that really makes people think a lot about those issues. So it's wonderful that you're doing that.
Thank you.
Just give it a second here if there's anybody who'd like to add anything or has any more questions. I know we're running a little bit over time. And a reminder that we have been recording. If you don't want your comments to be included at the end here, then just let me know and I can cut them out. Okay, awesome. So it sounds like that's about it for everybody. We will be in touch with the slides and everything. I might as well start my video again. Thank you so much, everybody, for joining. A huge thank you to Sébastian for doing this double header of a presentation bilingually. It's so wonderful and helpful. And he is a very friendly guy and an open book, and he'd be glad to hear from you if you have further questions or want to join a conversation. Like we said at the beginning, this is all part of a series of webinars, and you can sign up for the next 2 at the links I'm going to put in the chat right now. And further from that, the website that those links take you to is a community of practice or a community hub where any educators who work in climate change can stay in touch with everybody else. You can share resources that you have or ask questions or find others. So please do feel welcome to join and spread the word. Thank you, everybody. This is always so nice when at the end when there's all these thank yous in the chat. It's very hard.
Thanks everybody for being there, and some of you have met in person before, so you know what that looked like. But hopefully we can do that again in the future. And thanks, Tommy, for organizing this and doing all
I'm just so grateful. This is so fantastic. Like, you've spent a lot of time on this. Thank you so much. I guess I can pause the recording now too.
Probably.